You grab a pair of wireless earbuds, press the silicone tip into your ear, and instantly drop yourself into a perfect acoustic seal. Millions of people do this every day. We hit play and expect a flawless concert hall inside our heads, completely ignoring the mechanical ballet required to make it happen. To produce thunderous bass and crystal-clear vocals, manufacturers have to conquer fluid dynamics, acoustic resonance, and electromagnetic flux, all inside a space smaller than a AA battery. Delivering that level of acoustic fidelity on a global scale requires an industrial gauntlet operating on tolerances thinner than a single human hair. Modern earbuds represent a staggering concentration of high-precision parts, forcing engineers to solve complex physics problems inside a fraction of a cubic inch. The journey to create that sound begins with two extreme physical properties: raw conductive power and ultra-thin flexibility. First, the assembly requires an electrical nervous system. To build it, oxygen-free copper is drawn and stretched until it becomes a microscopic, hair-thin wire. Next is the magnetic engine. Dark, heavy neodymium powder is compressed into dense disks, forging some of the most powerful magnets on Earth. Finally, there is the acoustic piston. A sheet of PET plastic, thinner than a red blood cell, is stamped into a ribbed dome known as the diaphragm. Sitting on a factory floor, these elemental materials are entirely useless. To produce music, they must be married together with microscopic, zero-tolerance precision. This marriage happens inside the dynamic moving coil transducer. The hair-thin copper wire is spun into a tiny cylinder and glued directly to the edge of the plastic diaphragm. A robotic optical arm then takes this fragile copper assembly and lowers it perfectly into the center of the powerful neodymium magnet. This creates what engineers call the magnetic gap. Is the highly restricted space between the copper voice coil and the magnet walls, tightly controlled to be less than 0.1 millimeters wide. If this gap is too wide, the magnetic force fails to grip the coil effectively. The resulting audio is muddy and heavily distorted. But if the gap is too tight, the copper coil scrapes against the inner walls of the magnet, violently tearing the driver apart before it ever leaves the assembly line. Managing this chaotic electromagnetic push and pull within 1/10 of a millimeter is the true heart of manufacturing high-fidelity audio. But the mechanical driver is only the engine. To see how the sound wave takes its final shape, we have to look at the physical shell surrounding it. While the battery and printed circuit boards consume most of the internal space, engineers must precisely sculpt the remaining empty volumes and vents to guide the airflow. This graph reveals how software simulates the effect of those geometric changes. By digitally altering the nozzle length or the front volume, designers can see exactly how the audio frequencies shift before they ever cut a physical prototype. Once the physical dimensions are set, automated optimization routines take over. This visualization compares a target frequency response against the earbud's actual output, adjusting the density of acoustic meshes programmatically to push the performance as close to that target line as possible. These multi-physics simulations allow engineers to map the total sound pressure levels trapped and bouncing around inside the complex three-dimensional geometry of the casing. And housed right next to that carefully tuned acoustic chamber is the silicon brain. True wireless stereo microchips are packed alongside the driver to process spatial audio and active noise cancellation in real time. This diagram illustrates how those chips handle connectivity. By utilizing advanced mirroring technology, the system allows you to seamlessly transition between full stereo and single earbud mono, dynamically swapping roles between the left and right units without dropping the Bluetooth connection. Achieving the illusion of immersive three-dimensional sound requires perfect harmony between that physically tuned acoustic geometry and the digital processing power of the microchip. But all that digital tuning and precision assembly is useless if unwanted resonance creates distorted frequencies in the final product. On the testing line, automated rigs blast every single earbud with a full-spectrum audio sweep from 20 to 20,000 Hz, hunting for even the slightest microscopic turbulence. Yet the machines don't get the final say. Master acoustic engineers pull random units directly off the line and test them by ear inside heavily padded, completely silent anechoic chambers. They are listening for details a sensor can't fully contextualize: the warmth of a cello, the crisp decay of a cymbal, and a wide soundstage. It is a manual check to verify that the robotic micromachining is perfectly calibrated. Despite towering walls of automation and computational fluid dynamics, the ultimate judge of this microscopic manufacturing process remains the subjective human response to music. When you step out of the silent anechoic chamber and look at the packaging lines, the scale of this operation becomes staggering. Robotic arms weld, seal, and package thousands of finished units every single minute, moving at speeds the human eye can barely track. To put that volume into perspective, if you took a single month's production of that microscopic copper voice coil wire and unwound it, it could easily stretch from the Earth to the Moon. The modern earbud is born from a violent, chaotic process of chemical synthesis and magnetic alignment, tamed by extreme precision. When you press that silicone into your ear and the world fades away, you are hearing the result of millions of precise mechanical decisions, all perfectly coordinated inside a single plastic shell.